Hello, and welcome to Sleepy Science. Tonight, we're going to explore one of the most extreme experiences a human being has ever attempted. The moment we leave Earth and step into space, everything we rely on simply disappears. There is no air to breathe, no ground beneath our feet, no weather, no sound, no living world around us. Space is indifferent to whether we survive, and yet we go. We build rockets that burn with temperatures hotter than stars. We train astronauts to attempt what once seemed impossible. Against all odds, we manage to keep the human body alive in environments where biology itself begins to break down. Space travel is not safe. It is not natural. It is not easy. It is daring. It is frightening. And it may be the only path forward if we want to discover what lies beyond. If you enjoy these quiet journeys, you can gently support the channel by liking, subscribing, or leaving a thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, there is nothing you need to do except relax. Let your thoughts soften. Let your breathing slow. Allow yourself to drift gently toward rest. Let's begin. A spacesuit is in many ways a tiny personal spacecraft. It is far more than clothing. It is a self-contained life support system, carefully designed to keep a fragile human alive in a place where there is no air to breathe, no pressure to hold the body together, and temperatures that can shift by hundreds of degrees in minutes. Inside the suit, every layer has a purpose. The inner lining draws sweat away from the skin. The pressure garment gently compresses the body, preventing blood from boiling in the vacuum of space. The outer shell protects against razor-sharp dust and microscopic meteoroids traveling at extreme speeds. The helmet visor is coated with a thin layer of real gold, reflecting harsh sunlight. On the astronaut's back, oxygen tanks are paired with systems that remove carbon dioxide, circulate air, and pump cooling water through hidden tubes woven into the suit. Even the smallest tear in the fabric could be fatal. That's why every seam, every connection is checked again and again. To step outside a spacecraft or space station, an astronaut must place complete trust in this portable world. It is a small bubble of Earth carried into the endless silence of the universe. In space, astronauts can actually grow taller. Without gravity pressing down on the body, the spine is no longer compressed. The vertebrae slowly separate, allowing the spinal column to extend by several centimeters. At first, this can feel surprisingly pleasant, like a deep, gentle stretch after years of being slightly hunched. But the effect is not entirely comfortable. The back muscles must adjust to their new length, and astronauts often experience aches or even spasms during their first days in orbit. This change in height also slightly alters how the body moves inside a pressurized suit or a narrow sleeping bag. And when astronauts return to Earth, gravity takes over again. The spine gradually compresses back to its original form. This sudden shift can also cause discomfort. Mission doctors study these changes closely because they reveal how space affects bones, cartilage, and connective tissue. If humans ever build cities on Mars or live in large, rotating habitats in space, understanding how the body adapts to different levels of gravity will be essential for long-term survival. Space even seems to have a kind of smell, and astronauts can describe it. At first, this sounds impossible.
No one can breathe in space, so how could it have any scent at all? And yet, astronauts returning from spacewalks often notice a distinct zappac clinging to their suits and tools. Some describe it as the scent of hot metal. Others compare it to burnt steak with a sharp smell of welding fumes.
This unusual aroma forms when high-energy particles from the sun and cosmic radiation interact with the surface of a spacecraft. These reactions create reactive molecules that later mix with oxygen once back inside. When the airlock opens, astronauts do not smell space directly. Instead, they detect the chemical traces left behind on surfaces exposed to the vacuum. Scientists study these effects to better understand how materials degrade in space and how to protect sensitive equipment over long missions. In a strange way, this smell of space becomes one of the few sensory connections between Earth and the void. A reminder that, even in silence, the universe leaves its imprint. In microgravity, your body begins losing bone almost immediately. On Earth, bones stay strong because gravity constantly pulls against them, creating stress that keeps them dense and resilient. In space, that constant pull disappears. As a result, the body reduces the minerals it normally sends to reinforce the skeleton. Astronauts can lose nearly 1% of their bone mass each month while in orbit. This rate is far faster than even the most severe cases of osteoporosis on Earth. Weight-bearing bones, such as the femur and the spine, are affected first. Calcium that once strengthened bone tissue begins to enter the bloodstream and is eventually expelled through urine. This shift in minerals can also place additional strain on the kidneys. To counteract these effects, astronauts must exercise for several hours every day, using specialized machines that simulate resistance in zero gravity. Even with this effort, some bone loss is unavoidable. After returning to Earth, it can take years for bone density to recover, and in some cases, it never fully returns to previous levels. Preventing this weakening is one of the biggest challenges for future missions to Mars, where astronauts may spend years away from Earth. The Sun looks completely different when viewed from space. From the surface of Earth, the Sun appears soft and slightly yellow because our atmosphere scatters and diffuses its light. But beyond the atmosphere, the Sun becomes a sharp, blazing white sphere set against a perfectly black sky. There is no air to soften its brightness, no sky to scatter its light into gentle colors. Its heat arrives suddenly, without warning. Without proper protection, that radiation can damage materials and even burn skin within moments. Shadows in space are just as extreme. They are not soft or gradual. They are absolute, pure darkness with no fading edges. This intense contrast affects how astronauts perceive distance and depth. It also influences how solar panels absorb energy and how cameras capture images. Every space mission must carefully account for this raw, unfiltered light. It powers spacecraft, but it also threatens electronics and creates constant risk for anyone exposed to it. The Sun, seen from space, is a reminder that Earth quietly protects us in ways we rarely notice, surrounding us with an atmosphere that softens the harshness of starlight. Food in space must be carefully engineered for zero gravity. It cannot crumble, leak, or spoil easily.
A single floating crumb could enter a ventilation system and cause a malfunction. A drop of liquid could drift into sensitive electronics. To prevent this, every meal is designed with precision. Tortillas are often used instead of bread because they do not produce crumbs. Drinks are sealed in special pouches and consumed through straws. Fruits and vegetables are treated to eliminate bacteria, extending their shelf life. Even simple things like salt and pepper are dissolved in water so they cannot float away. Taste itself changes in orbit. Fluid shifts in the body can create a constant feeling of congestion, dulling the sense of smell and taste. Because of this, astronauts often prefer stronger flavors, spicy sauces, tangy foods, and sweet drinks.
Meals that seem normal on Earth can feel bland in space. There are no ovens or refrigerators on board, only food warmers and vacuum-sealed containers. Cooking becomes less of a creative process and more of a precise system. Each meal is a small scientific solution designed to nourish the body without introducing risk. Sleeping in space requires being secured in place. There are no beds, no mattresses, and no gravity to hold the body down. Instead, astronauts sleep inside soft, cocoon-like sleeping bags attached to the walls or ceilings of the spacecraft. Without these restraints, their bodies would drift freely, bumping into equipment or other crew members. The sensation of weightlessness can also affect dreams. Some astronauts report vivid experiences of floating or falling while asleep. For some, this is calming. For others, it makes rest more difficult without the familiar pressure of lying down. Lights are dimmed during sleep periods, but the environment is never truly quiet. Fans, pumps, and the occasional creaking of metal from temperature changes create a constant background noise. Sleep schedules are aligned with Earth time, even though the spacecraft may witness a sunrise every 90 minutes. Learning how to sleep in this environment is a skill that takes time, sometimes days or even weeks to master. Space travel requires rest, but it offers very few of the comforts we are used to on Earth. Even something as simple as tears behaves differently in space. Tears do not fall, they gather. Without gravity, liquid forms floating spheres. When a person cries, tears collect in the eyes, forming a growing pool that can blur vision and cause discomfort. Wiping them away is not simple either. A cloth tends to spread the moisture into smaller droplets rather than remove it. Sometimes tears drift toward the nose or become trapped under contact lenses, causing irritation. The only way to clear them is to blink repeatedly until surface tension breaks and the liquid separates. Crying in space becomes a strange and unfamiliar experience. Yet it is also deeply human. Even in orbit, emotions remain, and the way they are expressed becomes another quiet reminder of how far from Earth we truly are. Spacewalks are among the most dangerous activities astronauts perform. The moment an astronaut leaves the safety of an airlock and enters open space, every risk becomes real. A single, tiny tear in the suit could mean death within seconds. Temperatures can shift instantly from extreme heat to freezing cold as the astronaut moves between sunlight and shadow. Even the slightest push can send a person drifting away into the void. To prevent this, every movement is secured with safety tethers. Breathing itself must be carefully controlled, as the suit's atmosphere has to remain perfectly balanced to avoid oxygen toxicity or dangerous carbon dioxide buildup. Every tool must be fastened, every action rehearsed countless times in underwater training facilities on Earth. And yet, despite all preparation, spacewalks always carry unknown risks. The silence surrounding an astronaut during a spacewalk is not peaceful. It is the silence of a place where life does not belong. There is no up or down in space, and the human brain must adapt. In microgravity, the inner ear loses the signals it normally uses to maintain balance. The brain, suddenly deprived of this steady input, must create a new way of understanding orientation. Walls, floors, and ceilings lose their meaning. Astronauts may feel upside down, even when they are technically upright. Some adapt quickly. Others experience disorientation, nausea, or dizziness for several days. Simple actions, like reaching for a tool or turning a corner inside the spacecraft, can feel confusing until the brain adjusts. Objects no longer fall when released. Muscles no longer stabilize the body automatically. Every movement must be relearned with intention. This altered sense of reality is one of the most profound psychological challenges of living in orbit. Letting go of gravity changes not only how the body moves, but also how the mind understands the world. Space radiation poses a constant threat to human biology. Beyond Earth's magnetic field, the body is continuously exposed to cosmic rays, solar particles, and high-energy atoms traveling at extraordinary speeds. These particles can pass through skin, tissue, and even metal. As they move through the body, they can damage DNA, breaking strands and causing mutations. On Earth, the atmosphere protects us from most of this radiation. In space, that protection is gone. Astronauts receive radiation doses far higher than what is considered safe over long periods. This exposure can increase the risk of cancer, weaken the immune system, and even affect vision. Engineers are developing improved shielding for future spacecraft and habitats, but protecting the human body from invisible particles arriving from every direction remains one of the most complex challenges of deep space travel. Radiation is one of the major barriers standing between humanity and distant exploration. Even fire behaves differently in space. On Earth, flames rise upward because hot air expands and lifts, while cooler air sinks. In microgravity, this movement disappears. Flames no longer stretch upward. Instead, they form small, glowing spheres, soft, blue, and almost ghost-like. They burn more slowly and more evenly. Without gravity, smoke does not rise. It gathers in drifting, uneven clouds. This makes fires more difficult to detect and control. A small flame in a hidden corner could quietly fill a spacecraft with toxic gases before alarms even respond. For this reason, every material used in spacecraft construction is carefully tested for how it reacts to fire in zero gravity. Astronauts are trained to respond quickly, sealing compartments, shutting down airflow, and locating extinguishers even in confusion or darkness. Fire on Earth is dangerous. In space, it becomes unpredictable, moving in all directions at once. Astronauts must exercise every day just to stay alive. The human body depends on gravity to maintain muscle strength and bone density. Without it, muscles weaken rapidly. Leg muscles can shrink. Strength decreases. Even basic functions, like standing or breathing normally on Earth, can become difficult after long missions. To prevent this, astronauts follow strict exercise routines lasting several hours each day. Special machines simulate resistance in weightlessness. Some use elastic systems to mimic lifting weights. Others use harnesses and rotating devices to simulate running. These workouts are not optional. They are essential for survival. Researchers continue to study how to maintain physical health during missions that may last years. Without effective solutions, astronauts arriving on Mars might not even be strong enough to stand. In space, metal can fuse together without heat. On Earth, metals typically require high temperatures or welding to bond. In the vacuum of space, something different happens. Clean metal surfaces can stick together instantly through a process known as cold welding. Without oxygen or moisture to act as a barrier, atoms from one surface can bond directly with atoms from another. This can occur with tools, mechanical parts, or even small fragments of debris. To prevent this, engineers coat or treat metal surfaces that might come into contact. Otherwise, equipment could become permanently stuck. This phenomenon is both fascinating and dangerous. A robotic arm could lock in place. A panel might refuse to unfold. A hatch could fail to open. Cold welding is a reminder that in space, even basic physical interactions can behave in unexpected ways. Microgravity also changes how we experience taste. Food that seems rich and flavorful on Earth can taste dull or muted in orbit. Part of this effect is physical. Fluids shift toward the upper body, creating a sensation similar to nasal congestion. This reduces both smell and taste sensitivity. At the same time, the brain adapts to a new environment, recalibrating sensory input. As a result, astronauts often crave stronger flavors. Spicy foods, sharp sauces, and bold aromas become more appealing. Dishes that feel balanced on Earth may seem flat in space. Unexpected favorites, like shrimp cocktail with extra horseradish, become popular choices. This shift in taste is not just about enjoyment. It directly affects appetite, nutrition, and morale. For long missions, food must support both physical health and emotional well-being. Even a simple meal becomes part of the science of adaptation. Space sickness is similar to seasickness, but often more intense. The human balance system is designed to interpret gravity, motion, and body position together. Remove gravity, and the brain begins receiving conflicting signals. The eyes may see a stable environment, while the inner ear senses free fall. This mismatch can lead to nausea, dizziness, disorientation, and sometimes vomiting. Many astronauts experience space sickness during their first days in orbit. At times, it can make simple tasks like eating, working, or even sitting still unexpectedly difficult. To manage this, medical teams prepare astronauts with medication, controlled diets, and gradual exposure to activity. Over time, the brain adapts, but those first days can be uncomfortable enough to delay certain mission tasks. Returning to Earth can trigger a second wave of sickness, as the body must once again adjust to gravity. Space sickness is a reminder that even when we leave the planet, our bodies remain deeply tied to it. Inside a spacecraft, you can sometimes see what look like shooting stars. When tiny particles of dust or micrometeorites strike the outer surface of a spacecraft at extreme speeds, they release bursts of energy. These impacts can create brief flashes of light, visible from inside. Astronauts occasionally notice these tiny streaks while looking through windows or resting in dimly lit areas. These flashes may appear beautiful, but they are not harmless. Each one represents a high-speed collision, faster than a bullet. Over time, they create microscopic damage to surfaces like glass and metal. Mission teams carefully track areas with higher concentrations of debris and adjust flight paths when necessary. Even inside a spacecraft, humanity remains connected to the vast and active environment of space. Growing plants in space is difficult, but possible. Plants evolved under gravity, with roots that grow downward and stems that reach upward towards sunlight. In microgravity, these natural directions disappear. Water does not settle into soil. Air does not circulate in familiar ways. Seeds can sprout in unpredictable directions. Yet with carefully designed systems, astronauts have successfully grown lettuce, radishes, and even flowering plants in orbit. Special growth chambers provide light, nutrients, and controlled airflow. Water is delivered through mist or gel instead of flowing freely. Growing plants is not just a scientific experiment, it is essential for the future. Plants can provide food, produce oxygen, and help recycle carbon dioxide. They also offer psychological comfort, bringing a small piece of life into an otherwise mechanical environment. Watching something grow in space is a quiet reminder that life can extend beyond Earth. In space, blood flows differently through the body. On Earth, gravity pulls blood toward the lower body, and the heart works to circulate it upward. In microgravity, that pull disappears. Blood redistributes more evenly, often collecting in the chest and head. This causes noticeable effects. Faces may appear slightly puffy. Legs can look thinner. Blood pressure changes. The heart no longer needs to work as hard. Over time, it can begin to lose strength and muscle mass. After returning to Earth, astronauts must rebuild that strength. Doctors monitor circulation carefully to prevent complications such as fainting or abnormal blood pressure. This internal shift affects many systems, including vision and temperature regulation. Though invisible from the outside, every heartbeat becomes part of the body's adaptation to space. There is no true silence inside a spacecraft. While space itself is completely silent, the interior of a spacecraft is filled with sound. Fans circulate air. Computers hum. Pumps and valves click and shift. These sounds are essential. They are part of the life support systems that keep astronauts alive. Over time, this constant noise becomes familiar, almost comforting, a steady background reminder that everything is functioning as it should. But if a new or unusual sound appears, it can immediately signal danger. A sudden change, a rattle, a tone, A silence where there should be noise can trigger alarm. In space, silence is not peaceful. It can mean something has stopped working. The steady rhythm of machines becomes a kind of heartbeat for the crew. A constant reminder that survival depends on systems that must never fail. Some viruses behave differently in space. In the unusual environment of microgravity, radiation exposure, and altered human physiology, even microscopic organisms can change. Scientists have observed that certain viruses become more active in orbit. Samples of viruses, such as herpes or Epstein-Barr, have shown increased activity during space missions. In some cases, viruses that remain dormant on Earth can reactivate in space. This can happen even when astronauts appear healthy. Stress, disrupted sleep cycles, and changes in the immune system all play a role. This discovery has important implications for long-duration missions. If humans travel to Mars or beyond, managing microbial behavior will be critical. Understanding how life changes in space is not just about astronauts. It is about the delicate balance that supports all living systems. Even the smallest organisms remind us how closely life is tied to Earth. In space, even something as simple as washing becomes a complex process. A traditional shower is impossible because water does not fall downward. Instead, it forms floating spheres, drifting through the air like tiny liquid planets. To stay clean, astronauts use small amounts of water combined with no-rinse soap, gently wiping their skin with towels. Early attempts at space showers were abandoned because loose droplets would float into equipment, wires, and ventilation systems. Even washing hair requires careful technique. Water is massaged into the scalp and then absorbed into a cloth or evaporated into the air filtration system. Every drop must be carefully controlled and reclaimed. Water is far too valuable to waste. This routine is not only about hygiene, it is about comfort, identity, and maintaining a sense of normal life during long missions. Simple acts like washing your face or brushing your teeth become meaningful when every resource must be managed with precision. On the Moon, dust can be extremely dangerous. Lunar dust is very different from the soft sand found on Earth. It is sharp, jagged, and formed by billions of years of meteor impacts, without wind or water to smooth its edges. When it sticks to a spacesuit, it works its way into fabric, joints, and seals. It can scratch visors, damage equipment, and weaken protective layers. During the Apollo missions, astronauts returned to their lander covered in this dust. They described its smell as similar to burnt gunpowder. It irritated their lungs and clung stubbornly to surfaces. Future missions to the Moon will last much longer. That means managing dust will become essential for survival. Engineers are developing coatings and electrostatic systems designed to repel or remove it. Lunar dust may seem harmless at first glance, but in reality, it is a silent and persistent threat. Even cutting hair in space requires special tools. In microgravity, hair does not fall to the ground. Every cut strand floats freely, drifting through the air. These strands can enter eyes, lungs, or sensitive equipment. To prevent this, astronauts use clippers equipped with built-in vacuum systems. As hair is cut, it is immediately sucked into a sealed container. Even with these precautions, stray hairs can still escape, floating like tiny comets inside the spacecraft. Grooming is not just about appearance. It is essential for mental well-being. Maintaining personal care routines helps astronauts feel grounded in an environment that is otherwise unfamiliar. Even something as ordinary as a haircut becomes a small act of reclaiming normal life. Spacesuit gloves make every task more difficult. They are engineered with multiple layers to protect against vacuum, extreme temperatures, radiation, and micrometeorite impacts. But this protection comes at a cost. The gloves are stiff and resist movement. Fine motor tasks, like turning bolts or adjusting wires, can feel like working with thick winter mittens. The internal pressure of the suit pushes back against every motion. After hours of work, astronauts may experience bruising, blisters, or joint pain. Engineers continue to improve glove design, searching for better flexibility and control. Every small improvement makes spacewalks safer and more efficient. But the challenge remains. Space is not designed for human hands. Every movement becomes a reminder of how fragile the human body is in such an environment. Sometimes, tools are lost in space. During spacewalks, astronauts use dozens of tools, each carefully secured. But occasionally, something slips. When that happens, the object does not fall. It begins to orbit Earth. A lost tool becomes a tiny satellite, drifting silently through space. One astronaut once lost an entire tool bag, which remained visible from Earth for months. These objects may seem small, but they contribute to a growing problem: space debris. Each piece travels at tremendous speed and can damage spacecraft if it collides with them. Even a small object can become dangerous. Space may be vast, but orbital paths are becoming increasingly crowded. Tracking every object is a constant challenge. Every mission adds to this invisible cloud surrounding our planet. On Mars, every breath will have to be created. Mars does have an atmosphere, but it is almost entirely made of carbon dioxide. There is very little oxygen. The air is also extremely thin. Even taking a full breath there would provide almost no usable oxygen for the human body. To survive, astronauts will need machines that produce oxygen. These systems may split carbon dioxide into oxygen or extract resources from frozen water beneath the surface. They must operate continuously and reliably. Mars presents harsh conditions, freezing temperatures, dust storms, and radiation that can interfere with equipment. Future habitats will require backup systems, emergency reserves, and constant maintenance. Plants may help produce oxygen, but they will not be enough on their own. On Mars, breathing will not be automatic. It will be a technology. Every inhale will depend on machines working perfectly, and every breath will be a small victory of human ingenuity. For the first humans who travel to Mars, the journey may be one way. Reaching Mars takes many months of travel through space. Once there, the conditions, reduced gravity, high radiation levels, and extreme distance from Earth, create challenges far beyond anything humanity has faced before. Returning home is not simple. The fuel required to launch from the Martian surface would either need to be transported from Earth, which is extremely impractical, or produced on Mars itself using local resources. Even if that is achieved, the journey back would take just as long. Some mission concepts suggest that the first explorers may not return at all. Instead, they would remain, building habitats, growing food, and becoming the first permanent settlers on another world. After spending years in lower gravity and under constant radiation, their bodies might struggle to readapt to Earth. Bones, muscles, and organs could be too altered to survive the return. The decision to go to Mars may not just be a journey. It may be a commitment to stay. Not because return is impossible, but because survival after returning might be. Mars could one day become a new cradle of humanity, but it may require pioneers willing to remain there forever. Rocket fuel behaves differently in space. On Earth, rocket engines must fight against gravity and push through the resistance of the atmosphere. In space, there is no air resistance, no drag. This allows engines to burn more efficiently and reach higher speeds with less energy loss. However, this efficiency comes with new challenges. Without atmospheric oxygen, fuel must carry its own oxidizer to allow combustion. Flames behave differently in vacuum, and if something goes wrong, there is no air to disperse the energy of an explosion. Each engine burn must be calculated with extreme precision. A tiny miscalculation, just a fraction of a degree, can send a spacecraft off course over vast distances. Spaceflight becomes a delicate balance between power and control. Each ignition is a moment of commitment. Once a burn begins, there is no easy way to stop. The spacecraft continues forward, carried by momentum through a vacuum that offers no resistance. The faster the burn, the more precise the calculations must be. In space, there is no margin for error. Spacecraft must endure both extreme heat and extreme cold. When exposed to direct sunlight, a spacecraft can heat up to temperatures capable of melting certain materials. In shadow, it can freeze rapidly, colder than the harshest environments on Earth. There is no atmosphere to regulate temperature, no air to carry heat away or retain it. Only the emptiness of space, where energy is absorbed or reflected directly. To survive, spacecraft are designed with advanced thermal systems, insulating layers, reflective surfaces, and radiators help manage heat. These systems act like artificial skin, controlling temperature across the structure. Electronics must remain within strict temperature limits. Too hot or too cold, and they fail. Fluids must not freeze or boil. Even the spacecraft's orbit affects temperature, as it repeatedly moves in and out of sunlight. These cycles happen many times each day. The changes are intense, but the materials are engineered to expand, contract, and endure. Every mission begins as a battle against an environment that does not care if metal cracks or circuits fail. Space is a place of extremes, and every machine we send must survive both fire and ice. On Mars, sunsets are blue. On Earth, the atmosphere scatters sunlight in a way that makes the sky appear blue during the day and red or orange during sunset. On Mars, this effect is reversed. The thin Martian atmosphere is filled with fine dust particles rich in iron. These particles scatter red light away, allowing blue wavelengths to pass through more directly. As the sun sets, the sky around it takes on a soft blue glow. Meanwhile, the rest of the sky fades into warm shades of reddish-brown and muted gold. Because the atmosphere is so thin, the colors are subtle and dreamlike, almost like a watercolor painting. Future astronauts may one day stand on Martian soil and watch these quiet blue sunsets. They will be witnessing a sky no human had ever seen before the age of space exploration. It is a reminder that even familiar experiences, like a sunset, can become entirely new on another world. Space debris is one of the greatest dangers to modern space travel. Earth's orbit is filled with remnants of past missions, old satellites, fragments from collisions, paint chips, lost tools, all of it moving at incredible speeds, faster than bullets. Even a tiny fragment can puncture a spacesuit or damage a spacecraft. Larger debris can destroy entire vehicles. The more collisions occur, the more debris is created. This can lead to a chain reaction known as a debris cascade, a scenario where collisions create more fragments, which then cause even more collisions. If this process continues unchecked, it could make certain orbits unusable. Space agencies constantly track thousands of objects, adjusting spacecraft paths to avoid impact. Engineers are developing methods to remove debris, but the problem is growing faster than solutions. Space is vast, but the regions we use are becoming increasingly crowded. Every launch adds to the risk. Every mission must navigate a sky that becomes more dangerous with time. Astronauts train underwater to prepare for space. In a massive pool known as the Neutral Buoyancy Laboratory, full-scale models of spacecraft are submerged. Astronauts wear specially weighted suits that simulate the feeling of weightlessness. Underwater, movement becomes slow and deliberate. A small push can send the body drifting, just like in orbit. The water provides resistance, but also support. It is the closest environment on Earth to simulate working in microgravity. Here, astronauts rehearse every task: turning bolts, connecting panels, responding to emergencies. The training is physically demanding and mentally intense. Hours are spent practicing movements that must later be performed perfectly in space. This environment teaches precision, patience, and control. The underwater world becomes a gateway to space, a place where humans prepare to operate in a realm where even the simplest actions become complex. Time passes differently in space. Albert Einstein predicted that time is not constant, that it can stretch or slow depending on speed and gravity. And space missions have confirmed this. Astronauts aboard the International Space Station move at incredible speeds, while experiencing slightly weaker gravity than people on Earth. Because of this, time for them passes just a tiny bit differently. They age slightly slower. The difference is extremely small, fractions of a second over months, but it is measurable with precise instruments. If humans ever travel at much higher speeds, closer to the speed of light, this effect would become far more noticeable. A traveler could return from a long journey younger than those who remained on Earth. Time, in this sense, is not fixed. It bends. It stretches. It changes depending on how we move through the universe. Space reminds us that even something as fundamental as time is not as simple as it seems. Cosmic rays can create flashes of light inside the human eye. Some astronauts, while resting in dark cabins, have reported seeing brief flashes, even with their eyes closed. These are not dreams. They are caused by high-energy particles from distant cosmic events. These particles travel across the universe at nearly the speed of light. When they pass through the human body, they can strike the retina or optical nerves, triggering the sensation of light. The result is a flash, a streak, or a spark appearing in complete darkness. It can happen randomly, quietly, unexpectedly. Scientists study this phenomenon to better understand how radiation interacts with the brain and visual system. For future missions into deeper space, where radiation levels are even higher, these flashes may become more frequent. Even in darkness, the universe finds a way to be seen. On long missions, human bones may become dangerously fragile. A journey to Mars could take over a year each way, followed by extended time on a planet with lower gravity. During this time, bones steadily lose density. Without gravity providing resistance, the cells responsible for maintaining bone strength become less active. Minerals are released into the bloodstream and gradually removed from the body. Even with regular exercise, this loss cannot be fully prevented. After returning to Earth, recovery can take years, and in some cases, full recovery may never occur. If humans begin to live permanently on Mars, future generations may adapt to the weaker gravity. Bones could become lighter, more fragile, better suited to that environment, but less capable of functioning on Earth. This raises important questions, not just about survival, but about how humanity itself may change over time. Every tool inside a spacecraft must be secured. In microgravity, nothing stays in place. The moment an object is released, it begins to float. A loose tool can drift into ventilation systems, block filters, or collide with sensitive equipment. During spacewalks, the risk increases. A single lost tool can become space debris, orbiting Earth indefinitely. To prevent this, everything is attached, clipped, secured. Tools are labeled, tracked, and counted. There is no such thing as casually putting something down. Life in space requires constant awareness. Even the smallest object can become a hazard if left uncontrolled. Space toilets work using airflow instead of water. Without gravity, waste does not fall. Water does not flow. Traditional plumbing simply does not function. Instead, space toilets use carefully directed airflow to pull waste away from the body. Solid waste is collected and stored. Liquid waste is often filtered, purified, and recycled into drinking water. This system must operate continuously and reliably. Any malfunction could quickly become a serious problem in a confined environment. Using the toilet in space requires training and precision. Every component must be maintained carefully. Even the most private human activities become technical challenges. In space, survival depends on systems working exactly as intended. Solar storms can threaten entire missions. The sun is not always calm. At times, it releases powerful bursts of energy known as solar storms. These events send high-energy particles racing through space. On Earth, our magnetic field protects us from most of this radiation. But astronauts outside this protection are vulnerable. During a strong solar storm, radiation levels can rise rapidly. Within hours, they may exceed safe limits. To stay protected, crews must move into shielded areas inside the spacecraft. Often, these areas are reinforced with water or supplies, which help absorb radiation. Electronics are also at risk. High-energy particles can disrupt systems, damage circuits, or interfere with navigation. Future missions must include advanced warning systems and safe zones. The sun gives life, but beyond Earth, it also becomes a powerful and unpredictable threat. You could run around the moon's horizon in just minutes. The moon is much smaller than Earth. It has weaker gravity and a shorter circumference. An astronaut with enough speed and stamina could theoretically travel around the visible horizon quickly. Each step would feel different. Lower gravity would allow long, slow leaps. The ground would feel distant. The horizon would curve more noticeably. The sky would remain black, filled with stars, even during daytime. It would not be an easy run. The terrain is uneven. The suit is heavy and restrictive. But the idea reveals something important. Movement itself changes depending on where you are in the universe. Even something as simple as running becomes a completely new experience. A spaceship must carry its own atmosphere. On Earth, air surrounds us naturally. In space, every breath must be created, controlled, and preserved. Inside a spacecraft, the air is carefully balanced, a mix of oxygen and other gases. Carbon dioxide must be constantly removed. Humidity must be regulated. Temperature must remain stable. A single failure in these systems could be life-threatening. Every spacecraft includes backup systems, and even those backups have emergency modes. Astronauts also carry personal oxygen supplies in case of sudden failure. Future habitats on the Moon or Mars will expand these systems into entire artificial environments. Indoor ecosystems, where air, temperature, and pressure are fully controlled. In space, air is no longer something we take for granted. It becomes something we must build and protect every moment. The International Space Station never truly floats. It may appear to hover above Earth, but in reality it is constantly falling. It remains in orbit because it moves forward fast enough that as it falls, the curvature of Earth drops away beneath it. This creates a continuous state of free fall. Inside, astronauts feel weightless, not because gravity is absent, but because everything is falling together. There is no sensation of dropping, only a gentle, constant drifting. To maintain its orbit, the station must occasionally adjust its speed using thrusters or visiting spacecraft. Without these corrections, the thin upper layers of Earth's atmosphere would gradually slow it down. Eventually, it would descend. Orbit is not the absence of gravity. It is the art of falling forever while moving fast enough to keep missing the ground. Even the Milky Way has a kind of smell in a scientific sense. Certain telescopes can detect chemical compounds in interstellar clouds. Among these are molecules like ethyl formate, the same compound responsible for the scent of raspberries. Other regions of space contain traces of alcohol, complex carbon molecules, and even building blocks of life. Scientists translate these chemical signatures into sensory interpretations, allowing us to imagine what distant regions of the galaxy might be like. Though we can never smell them directly, these findings reveal something fascinating. The same chemical ingredients that exist in deep space also exist on Earth. In a way, the universe shares a common chemistry. Time dilation may shape the future of deep space travel. According to relativity, time moves differently depending on speed and gravity. Astronauts already experience this effect, though only slightly. But if humans were to travel at extreme speeds, close to the speed of light, time for them would slow dramatically. Years could pass for the traveler, while decades or even centuries pass on Earth. A journey through space could become a journey through time. Travelers might return to a world that is changed beyond recognition. This is not science fiction. It is a real consequence of the laws of physics. Time is not universal. It flows differently depending on how and where you move. After returning to Earth, astronauts must relearn how to walk. Months in microgravity cause muscles to weaken, bones to lose density, and the body to forget how to balance. When astronauts return, gravity feels overwhelming. Legs feel heavy. Movement feels unstable. Even standing can be difficult. Blood redistributes suddenly, often causing dizziness. Recovery takes time. Doctors and trainers guide astronauts through rehabilitation. They rebuild strength. They retrain coordination. Some astronauts use harness systems to practice walking safely. Others begin with short sessions before gradually returning to normal movement. This process can take weeks or months. It is a reminder that the human body is shaped by its environment. And when that environment changes, the body must change with it. Mars has storms that can last for months. The planet may seem quiet and still, but its atmosphere is active. Winds can lift fine dust into massive storms. Sometimes these storms grow until they cover the entire planet. During such events, sunlight is reduced to a faint glow. The sky becomes hazy. The landscape fades into muted tones. These storms can last for weeks or even months. Dust can clog equipment, block solar panels, coat every exposed surface. The particles themselves are sharp and potentially toxic. Future missions will need systems that can survive long periods without sunlight. Habitats must be sealed. Machinery must be protected. On Mars, weather is not just an inconvenience. It is a force that can reshape entire missions. Space medicine is still full of unknowns. We understand some effects of microgravity on bones, muscles, and circulation, but many long-term effects remain uncertain. Vision can be affected by fluid shifts in the body. The immune system may weaken. The brain may adapt in unexpected ways. Even wound healing may change. Each mission becomes a new experiment, a chance to learn how the human body responds to environments far from Earth. The deeper we go into space, the more questions we uncover. To live beyond Earth, we may need to rethink what it means to be human. Spacecraft must be built to withstand constant impacts. Space is filled with tiny particles, micrometeorites, traveling at incredible speeds. Even the smallest fragment can damage a spacecraft. To protect against this, spacecraft are built with layered shielding. These layers break apart incoming particles before they can reach the inner structure. Spacesuits are also reinforced, but not everything can be detected. Large objects can be tracked, small ones cannot. Every mission carries a constant, invisible risk. Traveling through space is like moving through a silent storm, where even the smallest spark can become dangerous. From orbit, Earth looks completely different. Astronauts can see entire weather systems at once. Storms swirl across oceans. Clouds stretch across continents. Lightning flashes silently within massive formations. Hurricanes appear as vast rotating systems. City lights glow softly beneath the clouds. From this perspective, Earth is not divided into countries. There are no borders, only landscapes, only motion, only a single interconnected system supporting life. Many astronauts describe a shift in perception known as the overview effect, a deep realization of how fragile and unified our planet truly is. From space, Earth is not just a place, it is a home. Spacecraft can accumulate electrical charge simply by moving. As they travel through Earth's magnetic field and pass through charged particles, static electricity begins to build up on their surfaces. This process is known as electrostatic charging. Over time, different parts of the spacecraft can develop different electrical potentials. If the imbalance becomes too great, it can discharge suddenly, creating sparks. These sparks can interfere with onboard electronics or even cause damage. To prevent this, engineers design systems that safely redistribute or release excess charge. In some cases, spacecraft even use this effect to generate small amounts of power. But it must be carefully controlled. In the vacuum of space, there is no air to carry electricity away, so every charge must be managed deliberately. Spaceflight turns even invisible forces into engineering challenges. Spacesuits are incredibly heavy on Earth. A fully equipped suit with its layered protection, life support systems, oxygen tanks, and communication equipment can weigh over 100 kilograms, sometimes even more than the astronaut wearing it. In microgravity, this weight is not felt. The suit floats along with the astronaut. But on Earth, training in such a suit is physically exhausting. Astronauts often train underwater or use special support systems to simulate weightlessness. Each suit is custom-fitted, designed specifically for the individual astronaut and the mission.
Even the gloves are highly complex, balancing protection with precision. A spacesuit is more than equipment. It is a personal spacecraft, a wearable system that carries everything needed for survival. In space,
it is not just heavy, it is essential. There is an ongoing debate about who owns space. For many years, space was considered a shared domain. International treaties prevented nations from claiming territory beyond Earth. But as technology advances, new questions are emerging. Private companies are planning to mine asteroids. Countries are preparing to build bases on the moon. Satellites are filling orbital space at increasing rates. Who decides what belongs to whom? What happens if one group claims a valuable resource first? The laws have not fully caught up with these possibilities. Space is becoming not only a place of exploration, but also of economics and politics. The future may require new agreements, balancing access, responsibility, and protection of a shared environment. Even breathing in space is a technological process. On Earth, breathing is effortless. In space, it must be engineered. Oxygen is either stored in tanks or produced through chemical processes. Carbon dioxide must be removed continuously. Humidity must be controlled. Air must be circulated. Every component depends on energy, materials, and careful design. If one system fails, a filter clogs, a pump stops, the atmosphere can quickly become unsafe. Breathing becomes something that must be maintained, not assumed. Each inhale is supported by machines, a reminder that life in space depends entirely on technology. Robots may build the first homes on Mars. Before humans arrive, machines could be sent ahead to prepare the environment. These robotic systems might use Martian soil, regolith, combined with binding materials to construct shelters. Some concepts involve 3D printing structures directly from local materials. This approach reduces the need to transport heavy building supplies from Earth. Robots could also install power systems, prepare landing sites, and set up life support infrastructure. By the time humans arrive, essential systems may already be in place. Mars could transform from an empty landscape into a prepared habitat, built not by human hands, but by machines designed to work in silence. Water behaves in strange and fascinating ways in space. Without gravity, it no longer flows or falls. Instead, it forms floating spheres. These droplets wobble, stretch, and merge like tiny liquid planets. Surface tension becomes the dominant force. Water clings to surfaces, to skin, to equipment. Astronauts cannot drink from open containers. They use sealed pouches to prevent droplets from escaping. Even cleaning becomes a careful process of controlling each drop. This behavior may look beautiful, but it also requires constant attention. In space, even something as familiar as water becomes something entirely new. Most astronauts bring a personal item with them. Despite the strict limitations of space travel, each astronaut is allowed a small object, a photograph, a ring, a small keepsake, something meaningful. These items are carefully packed among tools and equipment. Once in orbit, they serve as emotional anchors, reminders of home, of family, of life on Earth. When returned, these objects become more than keepsakes. They become artifacts, items that have traveled beyond our world and returned, carrying with them a quiet story.
In orbit, astronauts can watch a sunrise every 90 minutes. As the spacecraft circles Earth, the sun rises and sets repeatedly. Each sunrise begins as a thin line of light along the horizon. Colors shift quickly, from deep blue to orange, then to bright white. Soon after, darkness returns. City lights appear, storms flash. The cycle repeats again and again. Time begins to feel different, not measured by days, but by motion.
Sunlight never stays for long, and night never fully settles. Every space mission leaves behind traces of itself. Across the Moon, Mars, and even the empty stretches of orbit, humanity has scattered a quiet collection of objects. On the Moon, there are footprints, rover tracks, tools, flags, and even personal items left by astronauts. Because there is no wind or weather, many of these traces may remain unchanged for millions of years. On Mars, robotic explorers have left behind parachutes, heat shields, and the silent paths of rovers across ancient terrain. In orbit around Earth, abandoned satellites drift alongside fragments of metal, paint, and lost equipment. Some objects were left intentionally, others were lost. Together, they form a kind of accidental archaeology, a record of exploration written not in books, but in physical traces scattered across space. Future explorers may one day encounter these remnants, artifacts from the first steps humanity took beyond its homeworld. A spacecraft must function as a complete ecosystem. Unlike Earth, where air, water, and food are naturally available, a spacecraft must provide everything internally. Oxygen must be generated or stored. Carbon dioxide must be removed. Temperature and humidity must be controlled. Food must remain stable for long periods. Water must be recycled continuously. Even waste becomes a resource, processed and reused. Fire must be carefully contained, used only where necessary. Without gravity, systems must compensate through design, rotation, or exercise to maintain human health. The spacecraft becomes a small, artificial Earth, a closed system where every process is managed. Every failure has consequences. There is nothing outside to rely on. Inside, everything must work. You can hear a spacecraft. To those living inside, a space station is never silent. Air moves through vents. Fans run constantly. Systems adjust pressure and temperature. As the structure moves between sunlight and shadow, materials expand and contract, creating soft sounds, clicks, creaks, and subtle shifts. These sounds become familiar, almost comforting. They signal that systems are functioning, but any unexpected noise can signal danger. In space, sound is not just background, it is information. A change in rhythm can mean something has gone wrong. Astronauts learn to listen carefully, to understand the language of their environment. Spacesuits must be pressurized to sustain life. In the vacuum of space, the human body cannot survive without pressure.
A spacesuit creates that pressure artificially. It surrounds the body with a controlled environment, similar to Earth's atmosphere. But this pressure makes movement more difficult. The suit resists bending. Every motion requires effort. Engineers design joints and flexible materials to allow movement while maintaining protection. The suit also provides oxygen, removes carbon dioxide, regulates temperature, and shields against radiation. Without it, survival would last only seconds. A spacesuit is not just clothing. It is life itself, sealed around the human body. Venus is even more hostile than Mars. While Mars is cold and dry, Venus is extremely hot and dense. Surface temperatures are high enough to melt metal. The atmosphere is thick, composed mainly of carbon dioxide, with clouds of sulfuric acid. Pressure on the surface is about 90 times greater than on Earth. Landing there is like descending into a crushing, burning environment. Even robotic missions have survived only a short time before failing. Yet, Venus may once have had oceans and a more temperate climate. Studying it helps scientists understand how planets evolve and how environments can change dramatically over time. For now, it remains a place too dangerous for human exploration. Space agriculture may allow humanity to expand beyond Earth. Growing food in space is essential for long-term missions and future colonies. Without soil, traditional farming methods do not apply. Instead, plants are grown using hydroponics or nutrient gels. Light is provided artificially. Water is carefully recycled. On the International Space Station, astronauts have already grown vegetables and flowers. These plants provide not only food, but also oxygen. They help recycle carbon dioxide, and they offer psychological comfort, a connection to life. In future habitats on Mars or the Moon, agriculture will become a core part of survival. Food will not be delivered. It will be grown. Future space habitats may rotate to simulate gravity. One of the biggest challenges in space is the absence of gravity. Without it, bones weaken, muscles shrink, and the body changes. Instead of constantly fighting this, engineers may create artificial gravity. By building large rotating structures, centrifugal force can push objects outward. Inside, this force would feel like gravity. People could walk normally. Objects would fall. Life would feel more familiar. Concepts include rotating space stations or even large orbital habitats. These structures could support long-term living, families, communities, entire generations. If successful, they could become permanent homes in space. Not just places to visit, but places to live. Time behaves differently when you travel fast enough. According to the theory of relativity, time is not fixed. It can slow down or speed up depending on motion and gravity. For astronauts aboard the International Space Station, time passes slightly slower than it does on Earth. The difference is tiny, fractions of a second, but it is measurable. Clocks in orbit tick differently than clocks on the ground. If humans ever travel at speeds close to the speed of light, the effect would become much more noticeable. A traveler could experience only a few years passing, while decades pass on Earth. In a sense, moving through space also means moving through time. Space is filled with silence, but also with hidden signals. Although sound cannot travel through a vacuum, space is not truly quiet. Stars, planets, and galaxies emit electromagnetic radiation. Radio waves, X-rays, gamma rays, each carrying information. With the right instruments, these signals can be translated into sound. Astronomers have listened to black holes, pulsars, and even the faint echo of the early universe. What we hear is not sound in the traditional sense. It is data transformed into something our senses can understand. A hidden symphony, always playing, always present. The universe may be far larger than we can ever observe. There is a limit to how much of the universe we can see. Light travels at a finite speed, and the universe has a finite age. This means there is a boundary beyond which light has not yet had time to reach us. Everything beyond that boundary remains unseen, unmeasured, unknown. The observable universe is vast, but it may be only a small part of a much larger whole, possibly infinite, possibly structured in ways we cannot yet imagine. There may be regions forever beyond our reach. No signal from them will ever arrive, and no signal from us will ever reach them. In that sense, parts of reality may remain permanently hidden. Space exploration is also a reflection of human curiosity. Every mission, every telescope, every probe represents a question. What is out there? How did it begin? Where do we fit within it? These questions are not new. They have been asked for thousands of years. But now, for the first time, we are beginning to answer them directly, not just by looking at the sky, but by going there, touching, measuring, exploring. Each discovery adds to a larger story, a story that is still unfolding, slowly, carefully, across generations. One day, humans may travel beyond the solar system. Interstellar travel remains a challenge far beyond current capabilities. The distances are immense. Even the nearest star system would take tens of thousands of years to reach with current technology. But concepts exist. Nuclear propulsion, light sails pushed by lasers, generation ships that carry entire populations over centuries, or probes that travel at a fraction of the speed of light. Each idea faces enormous technical and physical obstacles, yet the possibility remains that one day humanity will extend its reach beyond the sun, into the wider galaxy, taking its first true steps into interstellar space. The story of space is not just about the universe, it is also about us, our desire to understand, to explore, to go beyond what is known. From the first observations of the night sky to modern space missions, this journey reflects something deeply human. A quiet curiosity, a willingness to look into the unknown, and to keep asking questions, even when answers are far away. As you listen, the universe continues. Stars are forming, galaxies are moving, time is passing, on scales both vast and subtle. And somewhere within it all, on a small planet orbiting an ordinary star, a mind is listening,
drifting, imagining, and slowly, perhaps, beginning to rest.